eddy current testing. Eddy current testing has been indispensable for a long time, both as a non-destructive material examination by hand and as a fully automatic method. Near-surface defects in workpieces can be tracked and specific material properties can be determined. How does eddy current testing work? It is based on electromagnetic induction. The animation shows a coil, which can be connected via an electric current meter to a voltage source. After applying a direct voltage to the coil, the electric current first increases fairly quickly, then more slowly, according to the inductance of the coil. Eventually it reaches a level resulting only from the ohmic resistance of the coil. The current creates magnetic fields that flow around every small piece of coil winding. The individual fields superimpose and form the total magnetic field depicted here in blue. If an alternating voltage is applied to the coil, the effective current through the coil is much smaller than when applying direct voltage. The reason for this is the alternating magnetic field, which generates a countervoltage in the coil by self-induction. The countervoltage in turn reduces the current consumption. Pushing an electrically conductive tube through the coil increases the effective current significantly. This is because the alternating magnetic field of the coil induces a current in the tube in circumferential direction, the eddy current. The eddy current in turn generates its own magnetic field, which counteracts the magnetic field of the coil. Consequently, the self-induction is low and the current consumption high. When a defect, for example a crack, comes into the path of the eddy current, the current consumption of the coil drops. The eddy current has to flow around the defect. The path of the eddy current is now longer, and the electrical resistance of the eddy current circuit is larger. This leads to a reduced magnitude and a reduced magnetic field of the eddy current. The self-inductance of the coil is increased, and the current consumption decreased. In practice, the alternating current frequencies are not as low as shown here for demonstration. They are much higher, typically in the region of some kilohertz. From now on, we're going to omit the magnetic field lines in the animation and represent the eddy current in a simplified static way. How does the technique work in practice? In eddy current testing with coaxial probes, the coils are either pushed coaxially over the workpiece or pushed through the workpiece. This is our simple test setup: the alternating voltage source, the electric current meter, the coil. Cables lead from the alternating voltage source to the electric current meter, then to the coil, and back again to the voltage source. Our sample is a tube made from an austenitic non-magnetic steel. We have purposely machined two cuts through the tube wall, one in longitudinal direction and one in circumferential direction. And here we go. The materials tester connects the return cable to the alternating voltage source. This closes the electrical circuit. The current consumption of the coil is still relatively low. Once the coil is positioned over the intact part of the tube, the magnitude of the current is high. The current decreases in the region of the longitudinal cut and reaches the original magnitude again in the intact part of the tube. The cut in circumferential direction has apparently no influence on the current. The animation shows the physical background. Low current consumption as long as the coil is still far away from the tube. The reason for this is the undisturbed self-induction. Much higher current in a region where the tube is intact. The reason here is the eddy current, its own magnetic field, and the reduced inductance of the coil. Smaller current consumption at the longitudinal cut, because the path of the eddy current is longer. The eddy current is lower and its magnetic field is smaller here. Full current consumption at the region with the saw cut in circumferential direction, as if there were no cut at all. The flow of the eddy current is almost undisturbed. Obviously, it is not possible to detect crack-like defects that run along the flow lines of the eddy current. Back in the laboratory, we observe the same phenomenon in reverse direction. This technique can be improved considerably if not only a single coil, but several coils are used. The original coil, which is now called the excitation coil, is supplemented with the receiver coil on the left side, and a receiver coil on the right side. A voltage meter is connected to each of the receiver coils. The improved test arrangement has been set up in the laboratory and is now in operation, as can be seen from the current consumption of the excitation coil. First, the materials tester picks up the right receiver coil and places it over the tube. The excitation coil is next in turn. As soon as he pushes it over the tube, the current consumption increases, exactly as in the previous test. Last in turn is the left receiver coil. He carefully takes all three coils and moves them to the right. The pointer of the right voltage meter deflects, then the pointer of the left voltage meter. Further to the right, where the tube is intact, the pointers of none of the voltage meters are deflected. Unfortunately, the saw cut in circumferential direction is again not detectable. The animation once more shows the physical background. The current consumption is high in an area where the tube is intact. The reason for this is the undisturbed flow of the eddy current. Because the magnetic field of the eddy current doesn't flow through any of the two receiver coils, we measure virtually no voltage on them. As soon as the excitation coil reaches the left end of the longitudinal saw cut, the current consumption decreases. The reason for this is the longer path of the eddy current. Because the eddy current now flows partly underneath the right receiver coil, its alternating magnetic field induces a voltage there. When the excitation coil reaches the right end of the longitudinal saw cut, the eddy current partially flows under the left receiver coil and induces a voltage there. Still further to the right, near the saw cut in circumferential direction, the eddy current is undisturbed. Its alternating magnetic field flows neither through the left nor the right receiver coil. The voltage meters indicate almost nothing. Back in the laboratory, we observe the same phenomena in reverse direction of movement. First, the pointer of the left voltage meter deflects, then the pointer of the right voltage meter. The technique can still be further improved if we use only one voltage meter, which is connected to the right-hand terminals of the receiver coils, and if the left terminals of the receiver coils are connected to each other. The voltage meter now indicates the difference of the voltages induced in the two receiver coils. We have set up this test arrangement in the laboratory too. The voltage meter clearly indicates the ends of the longitudinal saw cut. Unfortunately, even this arrangement cannot detect the saw cut in circumferential direction. If the coils are optimized even further, much smaller defects than our large saw cuts can be detected. This tube is made of a non-magnetic austenitic steel. 4 bore holes have been drilled through the tube, starting with a diameter of 1.4 mm and ending with 0.8 mm. Now, instead of performing the test by hand, we prefer to use a mechanized testing machine. The tube is firmly fixed in the testing machine on the right and the left side. After pushing the start button, the machine carriage moves several coaxial coils along the tube with the bore holes. By choosing appropriate test parameters and an optimized evaluation method, not only the locations of the holes along the axis may be determined. The diameter of the holes can also be measured approximately, a really neat feature. But one thing cannot be determined with this coaxial probe. It is the location of the defects in circumferential direction. Here we need another version, the eddy current testing with surface probes. We want to show this version in our laboratory too. Here the test piece is not a tube, but a sheet, again made of an austenitic steel. It has a saw cut in the middle, going right through the sheet. In contrast to the coaxial probes, the coil is not pushed over a tube, but instead placed with its flat side on the surface of the test piece. In defect-free areas, the current consumption of the coil is high. In the area of the saw cut, the current drops noticeably and reaches its full height again in the intact area. The same effect can be observed when the coil is moved across the saw cut from top to bottom. The animation shows that the current consumption is low when the coil is still far away from the sheet. This is due to high self-induction. As soon as the coil is placed on the sheet surface, the current increases. Once more, the reason is an eddy current that flows in the sheet in close vicinity of the coil. The eddy current again creates its own alternating magnetic field which counteracts the magnetic field of the coil and reduces the inductance. When the coil is located over the saw cut, the current consumption drops. The eddy current can no longer flow freely and must take a detour around the saw cut. This in turn decreases the strength of the eddy current. The magnetic field of the eddy current is weaker and interacts less with the coil. In the intact part of the sheet, the eddy current flows unrestrictedly again, and the current consumption of the coil is high. Eddy current testing with surface probes can also be refined by using not just one coil, but 3. The middle coil is the excitation coil. The 2 outer ones are the receiver coils. When all 3 coils are moved over the sheet surface, the pointer of the right voltmeter deflects first, then the pointer of the left voltmeter. And this is the reason. The current consumption of the excitation coil is high in an intact area of the sheet, where the eddy current flows freely. Because the eddy current path is slightly larger in diameter than the excitation coil, the magnetic field of the eddy current partially flows through the left receiver coil and already now induces a small voltage in it. In the same manner, a small voltage is induced in the right receiver coil. As expected, the current consumption is lower when the excitation coil is positioned on the left side of the saw cut. Now the magnetic field flowing through the right receiver coil is much stronger than before. Therefore, the induced voltage here is high. The situation is equivalent when the excitation coil is on the right side of the saw cut. The magnetic field of the eddy current now flows through the left receiver coil more intensely. The voltage induced there is correspondingly high. Although the technique with the arrangement of adjacent coils seems impressive, it has disadvantages. The local resolution is not particularly good, and very small defects are difficult to detect. We can achieve a substantial improvement with this layout of coils. The excitation coil remains unchanged. The right receiver coil is wound in the form of a capital D and sits within the excitation coil. The left receiver coil is laterally inverted. When testing this coil set in the laboratory, we are initially disappointed. Firstly, already in the intact region of the sheet, a high voltage is induced in the receiver coils. This is because the receiver coils are now positioned within the excitation coil. Secondly, the saw cut is only faintly detectable. Now we use a trick that we have already applied to the coaxial probes. We switch the receiver coils against each other and only measure the voltage difference between them. Now everything works in a way that suits us. Small voltage difference in the intact sheet, strong voltage fluctuations at the left side of the saw cut, and at the right side. But one point should always be kept in mind. The 2 D-shaped receiver coils must have the correct orientation for saw cuts and cracks. Otherwise you measure only little or nothing at all. If the orientation of cracks is not known, the probe is rotated by 90 degrees after the first pass and the test piece is scanned a second time. To demonstrate the basic principle, we have chosen rather large coils so far. However, the disadvantage of large coils is that only large defects, such as our rough saw cuts, can be detected. In practice, mostly very small coils are used, as shown in the example on the left-hand side. In this way, also small defects can be detected. The coils don't have to be round or D-shaped, but can also have a rectangular cross-section. Now let's take a look at the examination of a component in practice. As an example, we are going to inspect a bicycle crank arm with a crack. To do so, the materials tester uses a suitable eddy current probe. It has a tiny sensor with an excitation coil and 2 inner receiver coils on its tip. He carefully scans the surface of the bicycle crank arm with the probe. The monitor of the testing equipment shows almost no signal at an intact spot. But as soon as the probe scans over the crack in the crank arm, strong signals are visible. The right half of the monitor shows the complex impedance plane with the imaginary and real parts of the sensor signals. This version of eddy current testing is also well suited for mechanization. 3 very fine saw cuts with varying depths have been machined into this massive cylindrical rod in longitudinal direction. The rod is again made of an austenitic steel. The materials tester pushes the test piece with constant speed into the machine, so that the saw cuts pass through the actual test area. A look into the interior of the machine shows the rod in the centre. Here, the rod is not only scanned by just 1 probe, but in fact by 4. And each of the probes is equipped not only with a single coil, but with several ones. The probes are positioned radially at a small distance from the rod surface. During operation, they rotate around the rod at high speed. Meanwhile, the rod moves through the machine in longitudinal direction. Here, several frequencies are used for testing. Thereby, the penetration depth of the eddy currents can be varied. This helps to determine not only the location of the defects, but also their approximate depth. And this is where eddy current testing really starts.